Hello. In this video we're going to look at two final examples of curve sketching. So for the first one we have fx as x squared over x minus 1 squared. We have f prime given to us and f double prime. So we check really quick to make sure they're factored, and yep, looking at all of them, we don't have any quadratics that need to be factored, so we're good to go. Let's start in with the domain. So the domain of fx will be minus infinity to 1 union 1 to infinity. Again, for the domain, we're always looking at that denominator and seeing if we have any non-permissible values. Well, we could find the x-intercept and y-intercept, and in this case, again, they look like they're at the same place. The x-intercept comes from the numerator, which is at 0, 0, and that's also going to be the y-intercept, because the y-intercept comes from calculating f of 0, which of course is just 0 over negative 1 squared, or 0. So the x-intercept and y-intercept are at the same place. Now we can go ahead and find the horizontal and vertical asymptotes. So let's do the limit as x approaches infinity of x squared over x minus 1 squared. We're going to use the quotient theorem as always, giving us x approaching infinity, x squared over x squared, which is just 1. We'll check the limit as x approaches negative infinity of x squared over x minus 1 squared. Again, we use the quotient theorem whenever we're going to infinity or negative infinity, and that's going to give us also 1. So this tells us that we have a horizontal asymptote at y equal 1. Next up, we're going to look for that vertical asymptote, and the domain here tells us that we are likely to have a vertical asymptote at x equal to 1. We're going to, of course, need the sign diagram, but we can start it off down here. So we have the limit x approaches 1 from the left of x squared over x minus 1 squared. And we have the limit x approaches 1 from the right of x squared over x minus 1 squared. We'll save those actual answers until we get our sign diagrams. So over here we're going to do the sign diagram of f prime, and f double prime. So for f, we have, again, undefined at 1 and a root at 0. So we'll put those on. They're both even. Pick a number bigger than 1, say 10, positive, positive, positive. So that tells us that the graph will always be above the x-axis. Kind of interesting. Now for f prime, it looks actually we've got the same setup. We've got 0, and we've got 1. So pick a number bigger than 1. Oh, it's going to be negative. So negative, positive, negative. So the graph is decreasing, increasing, decreasing, which means we have a rel min. The other point looks like a relative maximum, but of course, because the function is undefined at 1, it's not a relative maximum. And we go for the second derivative. We've got a point over at negative 1/2. So we'll put that on. And then undefined, of course, at 1 again. This one is even. So we get positive, positive, negative. So that means concave down, concave up, concave up. And we get ourselves, right here, an inflection point. So we can go ahead and list, well, let's finish off that sign diagram here. So we're looking for x approaching 1, which means we're looking right here. And on both sides, it's actually positive. So for both of these limits here, we're going to have positive infinity and positive infinity. So we have a vertical asymptote at x equal to 1. Let's go ahead and do our increasing, decreasing business. So where is it increasing? decreasing, concave up, concave down. Well, it is increasing from just 0 to 1. It's decreasing on negative infinity to 0, union 1 to infinity. It's concave down on negative infinity to negative a half. It's concave up on a half to 1, union 1 to infinity. Next up, we can calculate the actual y values of the relative min and the inflection point. Now the relative min has already been done for us because we know f of 0 is just 0. So there's our relative min ready to go. But we do need to do f of negative a half. So again, I encourage you to pause the video here and give it a try. Alright, let's take a look at this one. Again, sometimes the fraction work can be the actual hardest part of these questions. You need to be very precise with your arithmetic here. Otherwise, of course, you'll get the wrong answer and it'll be really hard to get your curve. So we plug it into the original function, negative 1/2 squared over negative 1/2, subtract 1. So it'll give you a quarter over, well, negative 3/4, or 3/2 I should say, squared. So we'll get a quarter over 9/4, the 4's cancel, and we get 1 over 9. Let's go ahead and plot these points on a graph. So we've got our x and our fx. We've got our intercept, which also happens to be a relative minimum. We have an inflection point over a negative a half and 1 over 9, so maybe about here. This is going to be an inflection point. And we know that there is a vertical and horizontal asymptote, so there's a vertical one over at x equal to 1, so maybe about here. We've got a vertical asymptote, x equal to 1, and a horizontal asymptote at y equal to 1. Alright, so let's sketch the curve. Now, again, we know the graph is always going to be above the x-axis, so we're never going to drop down here. It's always going to be up here. We're going to be decreasing and concave down away from this asymptote. We're going to go through the inflection point and become concave up. We're going to increase to positive infinity on the side of the asymptote. On the other side, we're going to be coming down, decreasing, but still concave up and approaching these two asymptotes. So I think the easier part of this is on the right-hand side. This is going to just give us our classic swoosh. This side's a little trickier though on the left. We know we're going to go through the relative minimum like this and get almost a parabola type shape. But on the other side we have to be concave down, and so we should be something like this. Again, whether you draw it from the asymptote or from the point, it doesn't really matter, as long as it's coming in concave down here, and then switching to concave up down here. And again, you might be wondering, why are we crossing the horizontal asymptote here? Well, we've talked about it in class. You can always cross horizontal asymptotes, it's not a big deal. The point about the asymptote is as x approaches really far to the right, positive infinity, or as x goes really far to the left, negative infinity, we should be approaching the asymptote, which is what the graph is doing. For small values of x here, it doesn't matter what happens, it's not approaching either positive or negative infinity, and so the graph is free to cross the asymptote. Now let's do one final curve sketching example. We have f of x equals x over square root x squared plus 1. Now you might wonder, is the domain going to have some issues? Well, there's definitely a square root, which means you might have issues because you can't square root negative numbers. But x squared plus 1 will always be a positive number because 1 is positive, and when you square a number, you get positive or 0. So this is actually never going to be negative, which means you're good to go. The domain for this is negative infinity to infinity. Now we can go ahead and look that the x and y intercepts again happen to be at the origin. So the x-intercept is at 0, 0, and the y-intercept is going to be 0 over square root 1, which is also 0. Next up, let's look at those vertical asymptotes. Well, there are none, so we're going to need to do horizontal asymptotes. So we'll do the limit x approaches infinity of x over square root x squared plus 1. So use that good old quotient theorem. And we have x over square root x squared. Interesting. Well, the square root of x squared, we remember, is either plus or minus x, depending on whether x is going to positive or negative numbers. Right? The square root of x squared is equal to absolute value of x. So it's plus or minus x. In this case, x is going to a positive number, so we're going to get a positive value. So this will give us x approaching infinity, x over positive x, which gives us 1. And now we see why for all these questions we always have to do both the positive and negative infinity. As we go to do the quotient theorem, as x approaches negative infinity, we're going to see that we get the limit x approaches negative infinity of x over square root x squared. And in this case, as x is approaching negative infinity, the square root of x squared gives you negative x. Which gives us negative 1. So we actually have not one, but two horizontal asymptotes here. We have a horizontal asymptote at y equals to 1, and a horizontal asymptote at y equals to negative 1. It's going to be very important when we're graphing that we actually have both asymptotes. Now the vertical asymptote, well, there is none because there's no problems with the domain. So vertical asymptote is not applicable. Let's go ahead and draw those sign diagrams. So we've got f, f prime, f double prime. Now f only has one root, so we could just put that right in the middle at 0, and it'll be positive negative. Now what about f prime? Are there any values there? Well, there's nothing in the numerator, and the denominator you can't factor a sum of squares. So there's actually no roots, nothing to draw in the sign diagram. So you can pick any number. Sure, pick 10. 10 squared plus 1, and then cube it and square root it, you get a positive number. So f prime is always positive. Interesting. Which means the graph is always decreasing. Or sorry, always increasing. Now f double prime does have a root over at 0. So we get negative positive, concave up, concave down, and we are going to get ourselves an inflection point. But we already calculated f of 0, so we're good. We don't have to calculate anything there. We'll list, though, the intervals, because these are interesting intervals here. And, of course, they always ask you to list them on a test or on an exam, so we should get in the habit of it. So it's increasing on negative infinity to infinity. And it is decreasing. You can either say never, or you could put the empty set. Or you could say never. It's concave up on negative infinity to 0, and concave down on 0 to infinity. So let's go ahead and draw this graph. So we know there's going to be a point at 0, 0. 0, 0 is an inflection point. It's also both of the intercepts. And, well, that's the only point we have. We do have some asymptotes. We've got an asymptote at 1 and at minus 1. But that's all we're looking at in terms of information. So we have to be very reliant on those sign diagrams. Now the graph should be below the x-axis here and above the x-axis over here, based on the first sign diagram. Second diagram says we're always increasing, but we can't just increase forever up here, because, well, here's the logic. If we kept increasing and crossed the asymptote, then eventually we'd have to decrease and come back, because eventually we need to get to that asymptote. You can always cross them locally, but you have to approach them in the end, and we know the graph is always increasing, so that tells us in this case we're not going to cross the asymptote. We're going to increase and just slow down our rate of increase as we approach that asymptote. Now the graph is concave up here, so we should have up like a cup, and then down like a frown over here, but again, not so far down that we decrease away from the asymptote. So the graph is going to look like this. Increasing concave up, increasing concave down. It's almost like a sideways tan graph. So there you have it, the last example for curve sketching. Again, make sure you try those examples on the worksheet to get yourself really familiar with the different types of curves you can sketch. And I hope you enjoyed this application of calculus. As always, thanks for watching.